We are going to see now a couple of examples. The first one is the Cartesian product of two differentiable manifolds. We are going to see that it is also a differentiable manifold of the same degree of differentiability. And our second example is going to be the real projective space. It is interesting because it's not clear at all what it could be a natural embedding for such a manifold into some Euclidean space. So we're considering here two abstract manifolds, big M and big N, whose dimensions are respectively small m and small m. And we consider atlases of M and N respectively. Let us remind ourselves that U sub I is an open subset of M, V sub I is an open subset of R to the power small m, the dimension of big M, W sub J is an open subset of the second manifold N, big N, and B sub J prime is an open subset of R to the power N, okay? And we consider the following family. The family phi sub I times C sub J. What does that mean? It is written over here, the definition of such map. It sends a point x, y, x belongs to U sub I, and y belongs to W sub J, to, it's the obvious map. The first coordinate, which is in V sub I, is going to be phi sub I applied to x, and the second coordinate is going to be psi sub j applied to y. In this way, we have a homeomorphism. Here, we can give, for instance, the product topology that has a basis of open sets that consists of products of open sets of, a basis. If you consider the sets of the Cartesian product that are the following form, the product of an open subset of M and an open subset of N, you obtain a basis of open sets for the topology of the Cartesian product. So this map over here is going to be a homeomorphism, but it's going to be much more. It's going to be a CR atlas of the Cartesian product. And the proof, I'm going to let it to you as an exercise because it's really, really simple. It's just realizing how the fact that the phi sub i's form an atlas for M and the psi sub j's form an atlas for N can be combined to understand that these maps over here are the elements of an atlas of the Cartesian product. The calculations are fairly simple. Okay, what we can notice is that B sub I was an open subset of R to the power M, and V sub J prime was an open subset of R to the power M. So this thing over here is going to be an open subset of R to the power M plus M. So the Cartesian product is going to be a differentiable manifold if big M and big N are differentiable manifolds of differentiability class CR, then it's going to be also of the same differentiability class, and the dimension of the Cartesian product, as we all know, it's going to be the sum of the dimensions, as it happens, for instance, in linear algebra. All right? Now let's go to our second example, which is to be the projective space, the real projective space of dimension n. Let's give the definition, okay? We consider an equivalence relation in the complementary of the origin in R to the power n plus 1. And the equivalence relation is simple. Two vectors are actually related if they are collinear. It's just that. Okay, this is an equivalence relation, and the set of equivalence classes is going to be called real projective space of dimension n. And we are going to see that this is actually a manifold. There is an arrow map between r to the power n plus 1 minus the origin to the real projective space, which sends any vector to its equivalence class, right? This is just a map, which is of course surjective, right? And the primitive of a point is the set of vectors that belongs to the same equivalence class. We are going to define here some the domains of the local charts. Okay. So we consider first n plus 1 open subsets of our Euclidean space. Okay, and v sub j, j is going to vary from 1 to n plus 1, is going to be just the set of vectors whose coordinate of index j is different than 0. That's obviously an open set, and the union of all these open sets is the set of elements of r to the power n plus 1 that have at least one coordinate different than 0. In other words, what the space we're working with, the complementary of the origin in r to the power n plus 1. So that's great. And we consider u sub j as the set of classes of vectors in bj, okay? In that way, what we have is the real projective space is going to be the union of these n plus 1 sets, okay? And now let's work with that. We want to define the local charts. So let's define the inverses of the local charts, since that's going to be a little bit easier. What is the property actually that characterizes uj? It's that the j coordinate of a representative is always different than 0. Okay, we have to consider that if if we have an element, okay, that belongs to uj, this implies that x sub j is different than 0. And it doesn't matter what is the representative that we choose, because the other representatives are obtained by multiplying this one by some real number different than 0. So the fact of whether or not the coordinate of index j is 0 or not 0 is independent of the choice of the representative. So that's the property that have the elements of uj. But something that it is interesting is that they are always going to have, in every class that belongs to uj, there is always a representative whose j coordinate is 1. Because what you can do over here is dividing by x sub j. And since the inverse of x sub j is a real number, different than 0, of course, what you get is another representative. So we are going to exploit such a fact that in every class there is, and in every class in uj, there is a unique representative whose j coordinate is equal to 1, right? And in that way, we can give this parameterization of uj. Okay, the parameterization that is here. We consider an element of r to the power n. There are n plus 1 coordinates, but you have to see that we remove the one that have index j. So we have really n coordinates. This is a way that in which writing this expression is simple. And what we do is sending this vector to this class. This class is going to be in uj because the jth component is different than 0. And every class in uj is of that form. So this map over here is a bijection. It's a bijection between r to the power n and uj. We can actually study the coordinate changes because it is clear that there are classes, there are elements of the real projective space that belong to the domains of different charts. The minute that you have two coordinates that are different than 0, you are already in at least two charts. So we actually consider the expression of the coordinate change. Okay? So we have to consider phi sub j, the inverse of phi sub j, composed with phi sub k. And what we see over here is that we are sending first this vector to this class in the real projective space. And then we have to compose with phi sub k. But that's simply dividing all the elements, all the components, all the coordinates by x sub k, and then removing removing the one that you get in the k coordinate. It's exactly that. So what we're gonna get is this expression. You can actually do the calculations with a little bit of care. We're gonna get exactly this. And in this set over here, which is an open set, what we are going to have is that xk, x sub k is different than 0. So all these expressions are indeed C-infinity, are even better, are even real analytic because the denominator never vanishes. So the quotient of real analytic functions is still going to be a real analytic function. So that more or less implies that the real projective space is going to be a real analytic manifold of dimension n. There is just a very small problem, or not so small, depending on whether or not you can solve it. Is this space a topological space? Because if you take a look to our definition, we actually require space to be a topological space and these maps to be homeomorphisms and so on, even before defining the structure of differentiable manifold. So what can we do? What we can do is using the local charts to define the topology. Because, yeah, okay, so what do I mean by that? This map over here is a bijection. So you can actually use this bijection and the fact that there is a natural topology in this Euclidean space to give a topology in U sub j. But the problem is that in that way, for phi sub k, you're going to give a topology in U sub k, and so on. In every one of the UJs, you're going to have a topology. And what you have to check out is that these topologies that are defining the intersections of these UJs are the same. So when is that going to happen? If we have U sub j intersection with U sub k, this map has to be an open set. So that, and the way, if that happens, this image over here and the same and also the one in which we write here k have to be open subsets of r to the power n. Indeed, you can check out that that's the unique condition that we need. If that happens, the topologies are compatible. Okay, so that's what we need to know to check out whether the image by phi sub j of the intersection of uj and uk is an open subset of r to the power n for any choice of indices j and k between 1 and n plus 1. If we do that, it's over. Our projective space is going to be a real analytic manifold of dimension n. And what we can see is that the image of that intersection is the set of vectors in Rn, written in this way. Here there is a mistake because here it should be n plus 1, okay? But it's the set of vectors of this way such that the k coordinate is different than 0, and that's obviously an open set. So the topologies are compatible, and our projective space is indeed a real analytic manifold of dimension n. Let us remind ourselves that we defined an unreal map, the quotient map, from the complementary of the origin in r to the power n plus 1 to the real projective space. That sends any vector in its class. It's just that. Okay, we can check out whether or not this map is actually differentiable. What we have to do is consider this map. Okay, we have to compose to the right with the inverse of a local chart of r to the power n plus 1, but that we can consider that as the identity, and to the right with a local chart for our real projective space. So we have to consider something like that. And the expression that we are going to have is just this one. Of course, we have to define it for u sub j, but the expression is this one. And because of that, again, we have that this map is a differentiable map. It's a real analytic map. And obviously it's a continuous map. Something that it is interesting is that the fact that the map is continuous implies that the real projective space is a compact manifold. Because what we have is that the real projective space of dimension n is just the image of the complementary of the origin in r to the power n plus 1. But in every class, there is a vector whose Euclidean norm is equal to 1. So you can consider just the images of vectors of norm equal to 1. By multiplying the vector by some constant different than 0, we can actually change the norm to obtain another representative of the same class whose norm is equal to 1. It suffices to divide actually by the norm of the vector. But since the natural map is continuous and the sphere of dimension n, of any dimension, is compact, the image of a compact set by a continuous map is also compact. So this real projective space of dimension n is a compact real analytic, CW is for real analytic, manifold. And as I said, this is an interesting example because it's not very clear what could be the natural embedding of such a manifold in a Euclidean space. Okay? In the first few lectures, we treated the definition of a manifold, both from the embedded point of view and the abstract point of view. In the next lectures, we are going to discuss the infinitesimal properties of manifolds. We are going to define the tangent space at a point that is going to be a vector space of the same dimension as the manifold, and we are even going to define the tangent space of the manifold, the disjoint union of these tangent spaces of the manifold at any of its points. We're going to see that such a set is indeed a manifold. It's also a manifold. If M is a CR manifold, its tangent space is a CR-1 manifold. Besides that, we are interested not just in manifolds, but in the differentiable maps between them. And if we consider a differentiable map between open subsets of Euclidean space, we can actually define the derivative of such a map, or if you prefer, the differential. And we want to extend such definition to the case of differentiable maps between differentiable manifolds. We will do that, and we will see that the properties of such differential map are analogous to the Euclidean case. Indeed, we will see that the chain rule still holds. Thank you for your attention.